Okay, I've started the recording and now we will gradually move to this part, that is the 8086 architecture. Okay, so let me keep open this one, because if it will be suddenly closed then I will get to know. Okay, so 8086 is basically a family of microprocessor which was used, I think, on earlier, if I'm not make it wrong, earlier 90s. Okay, so it is 16-bit processor. 16-bit. So that means right now what we are using, that is a 64-bit processor. So it was the 16-bit processor. So an automatic question can be come in our mind. If this type of question anyone asked you, that what was the accumulator width, okay, or what was the accumulator data bit length in case of a 8086 microprocessor, what should be the answer?
16-bit.
16-bit. Okay, because it is quite common that your accumulator will hold the same number of bits what is actually being held by your microprocessor, or the same length actually I'm trying to say. So that means if we initially first target on the structure overall just this architecture, we will see some of the segment like different parts are there, some registers are there, okay, some different kinds of address generator, ALU, component, all things. So we will get to know what part is responsible for which purpose. Everything we will discuss. But first thing, we should make it sure that this part, when you are actually performing this thing like this CS, DS, SS, ES, so there are actually some segment or there are some registers or something like this. But what are the width actually? So everyone is 16-bit. Okay, so you can see that this stack pointer, base pointer, all these thing like these are also 16-bit. These temporary registers are 16-bit. ALU data bus are 16-bit. Only your address bus is 20-bit. Okay, so there are something. Now one more thing I should just inform you that this thing, the 8086 basic pin structure, pin, because our microprocessor always has some number of pins. If anyone has seen any processor at any time, or if anyone is using still the assembled desktop in their home, I don't know how much of you actually have used this assembled desktop in your home, because nowadays everyone is quite familiar with their laptop, and if desktop then also it is branded. So assemble lab desktop, there was actually the option like you will separately buy the microprocessor, you will own connect it, and the pins are there so you can see them. Okay, so quite interesting it was at a time. So this particular material, I have opened a new material right now, 8086 processor. This particular material will have some basic knowledge that which was your first generation processor, which was your second generation processor, like this. So I just give you a wrong information like early 90s. So actually this 8086 was used on during 1978, in this range. Okay. So now here you will get some pin numbers which was associated with every processors. 16 pins, 40 pins, then 64 pins, whatever may be. So here, after this some basic intro, you can get this pin diagrams. So some of the pins are there, which pin are actually for which purpose, the long story. Okay, so as you know that in our syllabus, some of the sections mandatory need to be kept as self-study mode. So we have kept this 8086 pin diagram only as self-study mode. Okay, so I will upload this material by today, and I will request you, according to your time obviously, you just try to read these pin diagrams. There are some notations you will get that GND, AD, NMI, INTR. So what are they actually? All the description has been written here. Okay. So once you will read them, you will get all the individual description there. So this thing actually not any type of like conceptual, or you have to get some calculation part. You need to know that how this calculation is being, or mathematical equation. This is not like this. This is just like some pins are there and what are their purpose, or what are their, why are they are situated. So something like this type of questions are there. Okay, pin diagram. So I will upload this material by today. Once I will complete this today's class, so I will upload this material and just read them. Okay, so here you will find something like address bus, data bus. So which pins are related to your address, which pins are related with the data. That means when you are passing some data, or when you are accessing some data, then through which pins it will come. Or we have done till now the addressing modes, so we know that how your addresses are accessed. So how your address will be communicated. So all these things will be done through these pins. Okay, so normally one 8086 microprocessor has maybe 40 number of pins, maybe 48 number of pins, maybe 64 number of pins. So three options are available. In our material, we have taken the basic one, okay, with 40 pins, and 40 pins structure has been discussed here. So if you want to get some more thing, or later when you will try to read it, obviously according to your choice, like some other material which is available from internet, if you get this pin diagram which I have shown it like 1 to 40, and if you get it like 1 to 64, no one is wrong. Okay, that processor having 64 pins, this 8086 processor having 40 pins. So just like the processing power, speed, everything can be varied. So your processor architecture also can be changed from processor pin chip to chip, like this. Okay, so this was the pin diagram, and here you will get some of the pins, how they are connected, how they are actually used, some of the input output operations. So every other individual details has been given. Okay, so it will be your task to complete them. And obviously I will be here, and you can ask anytime any question regarding this, that you have not understand the, maybe you have not understand the specific purpose. Like I can give you one example. Usually student ask this question, just like there is an option like minimum and maximum mode. Okay, so if you get some option like read, write, address, data, so quite easily you can just read them. Read means you are trying to again our previous discussion, that whenever you are reading, so that means you are just getting the data, you are fetching this data like this. And whenever you are writing, that means you are actually storing this data into this memory, right? So this read, write, data, address, hold, interrupt, all these things is physical. You can easily understand this thing. But most of the students usually ask this question, what is this minimum mode and what is this maximum mode? You are studying some processor part, right? Processor architecture. So in this part, how this minimum maximum will relate? So this is might be some question. Some students face this question as a confusing. Okay, so you also will read this. I can just give you some glimpse. Like whenever you will read this minimum or maximum mode, it is just like I think in desktop, whoever has used ever a desktop or some older days desktop, there was one option like safe mode. Safe mode. Okay, just like your system is creating some problems, your GP, your what I can say, your graphical user interface is not working properly. So you will select to run your system on safe mode. So once it will run in safe mode, you can do the minimum work that is required, right? Say you have started any Word document file, you have not completed it. Suddenly your GUI has created some problems, so you will open the system in your safe mode. You will just complete your minimum required operation and you will just shut down your system and you will bed. So minimum mode was that mode when you can do some minimum process. That means what is just need to be opened by your system and some minimum amount of operation you can do. That thing, whenever your processor can work in that mode, that is called the minimum mode. And maximum mode is normal. Just like right now I am discussing with you. What is open? My Microsoft Teams is open. Now in Teams there are 3 separate windows are opened. Parallelly, 3 PPT files are open. Parallelly, you can see here some text studio, that means the LaTeX window is also opened. My email window is opened. Okay, then some Word file is also open. So lots of things has been opened. So right now I am in maximum mode of operation. Okay, so now which task is said to be a minimum mode operation? That is also being mentioned as the pins. Some of the pins will also decide this. Okay, that these operations are should be operated in a minimum mode, otherwise it operates in maximum mode. Maximum mode is not, there is not any minimum criteria, but a minimum mode should have some minimum criteria, right? So this pin diagram you can read, it is not so much difficult, it is very easy. So I am directly moving to the architecture part. Okay, because if you open this architecture, you will get some of the difficult thing like AX, BX, CX, DX. We have almost know this AX, BX, CX part. What are they? Whenever we were doing this addressing mode, we were using a term like general purpose registers, index registers, all these things, right? So this AX, BX, CX, DX as the general purpose registers. Okay, on the left hand side. Then parallel, here is the address bus. You can see it is 20 bit. So your processor is 16 bit. You are using 8086, that is a 16 bit processor, that is fine. But this 16 bit processor can access a 20 bit address. How? That is also one matter of concern. We will also check this. Then data bus. So as your processor is 16 bit, so obviously your data bus will be of 16 bit of length. It can carry 16 bit of data. Now just when I show you this pin diagram part, initially you can see here this AD was written, right? Just like AD0 to AD14, that means how much? 15 numbers of, and parallelly 39, 38, 37, 36, 35. So here 5 more. So 15 plus 5, how many? It is 20. So 20 bit was there for this AD. So A for address, D for data. So the same pins are being used for address and data. But within this 20, 16 will be used for data. At a time, 16 bit can be used for data bus. But all 20 bits will be used for address bus. You can see that some of the address bus is associated with this S3, S4, S5, S6. Those are actually select bit. Okay, so those 4 bits will be extra. Now for S3, there will be 16 bit. For S4, there will be 16 bit address. For S5, there will be 16 bit address. Just like this data segregation will be done. Thus, your total pin can access total 20 bit of address. Understood? 4 extra bit will be acted as a select bit, S3, S4, S5, S6. That means for S3 there will be 16 bit address, for S4 there will be 16 bit address, for S5 there will be 16 bit address. Like this it will be operated. Okay, so that is the operation when you are performing this address bus along with this address generator. and this is the 20-bit address generator. So those are connected with some segments, CS, DS, SS, and ES. That is actually code segment, data segment, stack segment, and extra segment. Then the IP, the yellow line IP, you can see it is the instruction pointer. Again, one new term, right? Instruction pointer. But by processing, it is not new. We have already done this, done the use of IP, where if you remember in addressing mode or in just now what we have done in our lab also, this MIPS, we have seen this thing PC. What was this PC? PC was the program counter, right? And what we discussed in case of program counter, that program counter will store the address of next instruction to be performed, right? So instruction pointer is the same thing, just a different name. Actually, both are same. So sometimes they use their name IP, sometimes they use the name PC. So IP means instruction pointers that will also will point to the next available instruction. That means whenever you will perform the first, right now some instruction you are going to perform, so automatically your program counter has been updated, right? Or your instruction pointer has been updated. Anything you can take, any term you can take. So program counter will point to the next available instruction. Instruction pointer is also points to the next available instruction. So both are same. Okay. And the next part is internal communication registers, then parallelly bus control logic, some internal control systems, temporary registers. So all of the things are there. Now you can just observe that this whole structure has been divided top to bottom vertically into two segments, right? I am talking about this line. Okay. I am talking about this line. Okay. You can see this line is basically dividing our architecture top to bottom into two parts, right? So left hand section you can see what has been written, execution unit, and right hand side you can see it has been written bus interface unit. So that means this whole is being termed as execution unit, and the right whole is being termed as bus interface unit. You can see that all the buses like address bus, data bus, this is the bus control logic. That means here the control bus will be here. Okay, so all these things has been situated in this place, right? And all the registers like the general purpose registers who are actually perform the operations, those has been situated in this place. So this is the execution unit, this is bus interface unit. Now if you read some basic thing about them, what has been written, that means that bus interface unit fetches instructions, reads data from memory and IO ports, writes data to memory and IO ports. So this unit actually, say you have sit here, you are sitting here with your system, and this is your processor. So this bus interface unit actually will fetch the instruction from you through which part? Through the IO ports, because you may give instruction through this IO port, input output port, right? So that is one point. Then another thing, you have given instruction. So what will be done by this bus interface unit? It will check that what type of instruction it has to perform, right? So that means it will need data. So from where it will fetch the data? Simple thing. What we have already seen from the memory unit. So that means again this data bus will access this memory unit for the data. Then data bus has got this data, right? Address bus has got the address, that from which address it will perform. Data bus got the data. Then through some other unit, this will be passed to this direction. And this direction is the execution unit. That means what the operation is need to be performed through this instruction, that operation will be traveled from this direction to this direction here. Here you can see the internal control system. So this control system will send this particular operation to the specific place, that whether it is a logical or arithmetic unit operation, or it is just like some flag operation, like you have to stop, you have to start, or you have to check whether it is even parity or parity. So this type of operation is being termed as flag registers, or some temporary registers is being acting, whatever may be. The internal control system will specify this thing and will send them into proper location. You can see that this is a connection, this is a connection, this is a connection. Okay, so whatever bus interface unit is fetching, that data is executed by this execution unit. That thing has been written here, that EU executes instructions that have already been fetched by the BIU. Already been fetched by the BIU. And BIU and EU functions separately. So how separately they can work? You can see that there is an instruction queue. Okay, we will come in this section gradually. There is an instruction queue. So that means through this instruction queue, this data will be passed to this execution unit. Now this instruction queue performed in a pipelined manner. Pipelined structure. So what is this pipeline structure? Say right now I can take some name of the students, like here the first four, like Manisha, Dharvi, Aditya and Dev. So you are doing some project as a team. Okay, let us write the name Manisha, then it was Dharvi, then it was Aditya, and then it was Dev. Say U4 has prepared one team. For which purpose? Now you have the course like DTI. You need to form some team. So this 4 is a team. Now you have decided what type of task will be done by which person. Okay. Now here I can say any one of them, any one of you, say this person is very efficient in coding. Say this person is very efficient in writing. Writing means report writing. Say this person is very efficient in presenting. That means when you will you have completed your work, and when in the final presentation is going on, then Dev is the actual person who can present in best way. And what I have just considered, that it is coding, and Aditya is responsible for writing the report, and Dev is for presentation. So and Manisha was responsible to identify the data. That means she is very much efficient in analysis phase. That what type of work you should do, in which approach you will go. So the analysis and design phase can be very much done by her. So these 4 process you have separated. That means you will do this, I will do this, I will do this, I will do this. Now think that your project has some modules. Say 4 modules you have. So for each module, Manisha need to do the analysis part. For each module, Dharvi need to do the coding part. For each module, Aditya will prepare the report separately. And for each module, they will be also preparing the presentation part. So now think that everyone is related, right? Just like if Manisha has not prepared his analysis phase, Dharvi cannot start coding, right? Then Dharvi, unless complete the coding, Aditya cannot start the report writing. And if all these things has not been completed, then how you will present? It is quite common, right? So that means this thing you have to wait for Manisha's work. Manisha has completed, then Dharvi will start coding. Then Dharvi will complete, Aditya will start coding. Aditya will complete, they will start writing, or they will start presenting. So all these things are just dependent on each other. So pipelines say you that no need to depend to complete the whole task. You have 4 modules, so you can break the module. Just like say Manish has completed writing the first module. First module she has completed, right? So then she will pass this first module to Dharvi for coding. So now Dharvi is writing the coding part of the first module. So once she has completed the coding of first module, she has passed this data to Aditya. Now think, when this first module has been passed from Manisha to Dharvi, so Manisha is free now. So she can start the second module, right? Once Dharvi has passed the first module of coding to Aditya, then Dharvi also is free. So at that time, Dharvi can start the second module of coding if it is passed by Manisha. So that means every time some of the person can work using some on some of the module. So no one need to be sit idle. Yes, you need to sit idle for the first task, because for the initial task there will be some little bit of amount of time. That time will be taken by Manisha and she will pass it to Dharvi. Dharvi will pass it to Aditya. Aditya will pass it to Dev. So this time will need to be waited. But later everyone can work simultaneously. Okay, so BUI when will pass this instruction to the execution unit, they will follow one queue, this instruction queue, and this instruction queue will work as a pipeline manner. That means for the first instruction, if it is being executed by the instruction execution unit, BIU can be working or can be engaged himself for this second unit of task. It is quite common, right? So that is why it has been written that their functions are separate. They may be related, but they are separate. Okay. So this is the basic structure. Now if you go to the details discussion that how this individual unit actually do. So in the bus interface unit you can see that this thing, this address generator is dedicated to generate 20-bit address, right? 20-bit address. But our processor is of 16-bit of length. And here you can see 4 16-bit segment registers. So these are actually segment registers, okay? Code segment, data segment, stack segment, and extra segment. So if you gradually move to the part like which segment is responsible for which task, you can see according to the diagram, it is quite common that whenever you are taking this term like segment register, so obviously it is just like creating some segments of your work that for one particular task can be divided into how many segments. So here some example has been given that if you try to segment your work or if you try to distribute your work into some parts, so how you can distribute, just like 1 megabyte of memory of an 8086 microprocessor is divided into segments of size up to 64 kilobyte each. That is only for example, right? 1 megabyte of memory of 8086 microprocessor is divided into segments of 64 kilobyte each. That means 4 segments you have created, 64, 64, 64, 64. Just like. Now the next thing is how they can be stored or how they can be situated. So at any particular time the 8086 can directly access 4 segments. Okay, at any particular time, the 8086 can directly access 4 segments. That means 256 kilobyte within the 1 megabyte of memory. So you are considering your total memory access will be 1 megabyte. You are creating some number of segments of size up to 64 kilobyte each. But at a single time, that means at a single instant, So how we will control this time or this instant? How we can control? Again the clock pulse, the older thing. So here you can see everything is related to each one. We have done the clock pulse previously. Right now I am getting this term like at any particular time. So who will control this time? You will not take your watch and you will say that yes, 15 seconds is over, so you will stop working. Like this, it is not working. Right? System has its own clock pulse. So one pulse will be passed, it will count that yes, 1 unit of time. Next pulse, another unit of time, like this. So in any particular unit of time, uh, this 8086 can directly access 4 segments. So that means how many total space will be there? It is obviously 256 kilobyte within 1 megabyte of memory, right? Then the next thing is program obtain access to code and data in the segments by changing the segment register content to point to the desired segments. So that means here you can see some of the segments has been mentioned like segment 0, 1, 2, 3, 4, anyone, and physical memory is also there. So this segment is actually pointing to that location, this segment is pointing to that location. Some of the segments are overlapped, some are partially overlapped, someone is fully overlapped, okay, someone is disjoint. So all of the possible can be there, right? So this is actually the segment register. Whenever you will just creating this different type of segments, so segment registers will change the segment register content to point. That means again just like of instruction pointer type of thing, that your one segment is working, that means at that time your next segment pointer will be ready, that after this point where you will access or where you will go. This type of relation, this type of segmentization, okay, that from one segment which desired location you will move, like this it is working. So the next thing we will see that code segment registers. So till now we were discussing only the segment registers, so all of them are segment registers, right? This code segment, data segment, stack segment, extra segment, all of them were segment registers. And you have just seen that how your segment registers are accessing, like at a single time of instant 64 kilobyte of one segment and maximum 4 segment you can access. All these things you know now. But now you will go to more deep section, just like who is the code segment register, who is the data segment registers, so all these things, right? So once you are reading these code segment registers, you can see that code segment contains the base or start of the current code segment, right? So code segment register is also of a 16-bit registers. What is the task of this code segment registers? Now it will store the start of your current work. So if you now relate this with your MIPS programming, 3 sections were there. Okay, just like if it is open till now, I can show you. Yes, it is open. So 3 sections were there, right? Apart from this temporary register, kernel registers, just like GP, SP, and FP. So GP was pointers to global area, SP was pointer of stack, FP was frame pointer. So that means these are just like these code segment registers. You know from these registers that from which location you will start your work. Okay, so that means code segment contains the base or start of the current code. Instruction pointer contains the distance or offset from this address to the next instruction byte to be fetched. So you are saying that yes, my code segment is holding the base address. So who will inform your system or who will inform your processor that yes, your code segment is holding that address, so you have to move to that address? Who will be responsible for this? Obviously your program counter, or in this term it is instruction pointer, whatever maybe you like, same thing, right? The next thing is BIU computes the 20-bit physical address by logically shifting the contents of CS4 bits to the left and then adding this 16-bit contents of instruction pointer. So what is this thing is being mentioned? This second line, this second row is can be create confusion for you all. What was my address generator length? It was 20-bit address bus, right? And what we are seeing, that when you are using this code segment register, 16-bit code is specified for your current code segment, right? Now the BUI computes the 20-bit physical address. BIU computes 20-bit physical address means the physical address which is accessed from the memory or anywhere, 20-bit physical address. So how this 16-bit will manage them, right? So this 4 bits to the left, that means extra how many bits are there? 4 bits. So code segment 4 bits to the left. So it will send like this. Let's say this here 16 bits data is there. Now your this address generator having 20 bits. So 4 more extra bits are there. 1, 2, 3, 4. Right. So at a time, any one of them will come to the first position of this. That means the left position of this code segment register. And first one has come. So for this one, 16-bit has worked. Then for this one, 16-bit will work. Then for this one, 16-bit will work. So just like this 20-bit will be managed. And who will manage all these things? Obviously, your instruction pointer will manage all these things. Because first, which of the code segment will come, then which of the code segment will come. So all this tracking or all this managing part, like maintaining the sequence. So all of these things is done by this code segment registers. Instruction pointer, sorry. So that means all instruction of a program are relative to the content of the code segment registers multiplied by 16, and then offset is added provided by the IP. So that is the thing, offset. So that means the 16-bit what you are using in normal way, that is 16 bits perfect. All the 4 extra bit is your offset. So literally you are accessing 20-bit address, because these offsets are gradually controlled by the instruction pointer. First offset 16-bit address, second offset 16-bit address. So like this they are actually continuing. This was the code segment register. Then the next one is the data segment register. Okay, so data segment register also obviously 16-bit, points to the current data segment. Operands for most instructions are fetched from this segment. 16-bit contents of the source index or destination index or a 16-bit displacement are used offset for computing this 20-bit physical address. So that means again, if you are thinking that you are using data segment register, so data segment, that means always will be ready for the 16-bit data, that is not any problem. But now this data can be used for some operation, and how these data are being used for some operation, it can be fetched from the memory, just like source index addressing. Whenever we were using this MIPS instruction format, 3 address was there, like destination, like source argument, like the second argument. So all of these things were there, right? So that 16-bit contents of the source index and destination index or a 16-bit displacement are used as offset. That means whether you are using the source index or you are using the destination index or you are using the displacement index, so those are the tasks of the index register actually. That thing also will come later. Okay, so that will be the offset, and those will be integrating your data segment registers along with this index registers, and your 20-bit physical address will be managed. Okay, so then the next part is the stack segment. So stack segment, still now we have not in detail discussed, but here some of the discussion can be done. Just like whenever you will use a stack type of information storage, okay, and then every space of length must have 16-bit of length, so it is 16-bit, right? So stack segment register, just think the name, stack segment register. So obviously this register will point to some stacks. So where it will point, it will point to the current stack, that from which location you are just now working, if it is a stack type of storage or stack type of location. Then 20-bit physical stack address is calculated from the stack segment and the stack pointer for stack instructions such as push and pop. In based addressing mode, 20-bit physical stack address is calculated from the stack segment and base pointer. So that means again the 16-bit of data you can handle. So again some 4-bit extra informations are there. So who are controlling those extra bits? The stack segment register, stack pointer, base pointer, all of them. So what is the common thing you are observing? We are observing that first we were doing this code segment register, then we are performing this data segment register, then we are performing this stack segment registers. But every time you can see that every time some of the offset bits are there. Offset bits, right? Those who are actually controlling the extra bits that is associated with your what I can say, that is associated with your address, the 20-bit physical address. Okay, 20-bit physical address. So now when you will calculate the next part, like which one is pending? We have covered code segment, data segment, and stack segment. So the last one is extra segment. Extra segment. Okay. So here what it will be done? Now we have already seen that at a single time you can create one segment of 64 kilobyte, right? And at a single instant, 4 of them can be accessed. But segment can be created, large number of segment can be created. So who will store this number of segment information? That information will be stored by this extra segment register. Segment registers points to the extra segment in which data is stored. Now in data means in excess of 64K pointed by the data segment register. So string instructions use this extra segment and data instruction to determine the 20-bit physical address for this destination. Okay, so it is actually not DI, it should be DS. It has been done a mistake by me. Okay. So that means we can see that our code segment, data segment, stack segment, and extra segment, 4 of the segment registers were there, and 4 segment registers are handling this at 20-bit physical address by their own virtue, by their own style, by their own pointer. So every time some code segment registers or some instruction pointer is responsible to doing this thing. Now each of them has some separate task. So all the task has been discussed. You just read them and get an idea that how your system's segment registers are situated. Then the next part, if you see, that is the instruction pointer. We have already known that what is the instruction pointer. So till now what we are doing, all of these things are the part of bus interface unit. You can see from the right hand corner. Every time we are doing something, but bus interface unit is fixed. So all of them are the part of bus interface unit, right? The instruction queue also has been discussed previously. That how I have just give you the example that how this instruction queue will work, how the pipeline will work. Okay, so these are the part of your bus interface unit. These were. And the last one is actually pending, that is the execution unit. Today I will not start this execution unit, but execution unit is not too much difficult. Some of the registers, which registers are being used for some purpose of your operations. So these operations may be a control operations, like which will decide that what type of instruction will be performed, and then the processing operation like ALU operations, what type of arithmetic or logical function will be done. So you have seen that already. We have told internal control system can access this ALU part or temporary register part or flag registers part, and what type of work will be done. Okay, only the thing need to know that here we can see that every registers like AX, BX, CX, DX are divided into 2 segments or 2 parts, like AH and AL, BH and BL. So who are they actually? These are obviously the part like high, that means the higher bit, higher order data and lower order data. Just like we have done this in case of multiplication, the HI and LO. Higher order result were stored in HI part, lower order result were stored in LO part. So just like the same. So AX, BX, CX, DX. So whenever you will multiply some operation or multiply some instruction, you will perform between the registers like AL and AH will be responsible to store the data. So this thing we will discuss on the next day. So some of the 16-bit registers who can use as two 8-bit registers just like AX, BX, CX, DX. That is AH, AL, BH, BL, CH, CL and DH, DL, and some index registers. Okay. So you can see here those index registers, source index, destination index. So we have already discussed this thing in case of the segment part. That you are saying that your data segment registers is there and it will be divided into source index, destination index, and at a time by instruction pointer this 20 bits physical address will be maintained. So where are the registers actually? So registers are actually stored in this left hand side. The index registers, you can see this point here. Okay. So some general purpose registers where they are, some index registers where they are, just like here SP is for stack pointer, BP is for base pointer, DI for destination index and SI for source index. So all of them are basically registers. Okay, so tomorrow I have class? No. Oh, this week class has been done. That means Monday when we will start, Monday, this 8086 execution unit will be started from Monday. Okay, and you just read in between time if you get time, apart from all the other your business, because you have a tight schedule always. So if you read something and if you get that something can be discussed again, or you are facing some difficulties to understand some of the points, then obviously we can discuss it again, no issue. So that's the end for today.